Hello everyone, and good morning. Welcome to the OneClass channel. My name is Fejiro, and I'm an Honors Bachelor of Science graduate working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some homework help or some tutoring or just some extra hands-on help in regards to understanding some materials, please check out the links in the description below. That way we will be able to assist you at your earliest and best convenience. With that being said, let's hop right into this session for today. And that would be starting with question 1. And this question, we're starting relatively light. We're going to start with this. How do you convert 1 gallon to, so 1 gallon to quarts? Alright, so to solve this question, the goal here is to make sure that we are converting the right thing that they ask for. We start with 1 gallon, so that would be what we put on the left. Okay? And then the goal here actually in terms of the conversion sheet is to make sure that the units cancel out appropriately so that you end with quarts. That's the goal there. So with that being said, according to the unit conversion sheet here that I have, for volume, 1 quart would be 0.25 of a US gallon. So if we did that, we would have 0.25, gallons, and it says 1 quart, for at least a liquid quart, which is I assume what this question is asking here. So with that being said, it means that for this 1 gallon, we're going to divide it by 0.25 to get the answer, and you'll see that it's actually 4 quarts. So with that being said, there are actually 4 quarts in a gallon, assuming that this is what they're referring to. Yeah. So with that being said, this is correct. All right. So now that we've gotten that warm up, we're going to start delving into a little bit more complicated questions, starting with as well, what is the electron configuration of oxygen? Okay, so to do electron configuration, it's important to note down our shells. So I have the 1s, 2s, 2p, 3s, 3p, 3d. Each of these corresponds to a certain number of elements on the periodic table. So if we wanted to start at the 1s, for example, I'm referring to the hydrogen and helium. So think of it as we're literally counting through the elements in order to be able to get over to where we want to be for oxygen. So hydrogen would be 1s1, The s subshell can only take 2 electrons. So hydrogen would be the first element that has 1 electron, and helium would be 1s2. So we've crossed over the hydrogen and helium. So we know that now for oxygen, it has at least 1s2. So now let's go down to the next row. Lithium would be the 2s1, because now it's the second row, and then we're still in the s orbital, the s subshell. So it'd be 2s1, and then as well beryllium would be 2s2. So we've actually now crossed over the lithium beryllium, so we know oxygen at least has 2s2. And then we enter this side here, columns 13 through 18. Excluding helium, these are your p subshells as I've listed here. and oxygen is the fourth one on this row. So if we count boron, that's 2p1, carbon will be 2p2, nitrogen would be 2p3, and oxygen would be 2p4. This is how you'd find the electron configuration for for oxygen, sorry. Because what we've done here is that we've gone through and counted, okay, based on the periodic table, counted and be able to get to this value. The important thing is recognizing which subshell you're in, okay? Because as I stated earlier, the S subshell would be the first and second column, okay? That's how we, and including helium, because it's technically in the S column. And then the second subshell, the P, would be between 13 and 18, those columns, not including helium. And then as you see here, I also have like a 3D, for example. Your D subshells are actually the transition metals, typically between columns 3 and 12. And then there's also another subshell, but we don't really need to discuss that right now. The important thing is knowing how to count through, because you're literally going to be, if you're ever unsure, just count through each element, notice which notice which element number whatever you're trying to find is, and make sure that these values here should add up theoretically to your element number. Oxygen is the 8th element, and as you can see, if I added the 2, 2, and 4, I can say that yes, this represents oxygen because of the fact that I have 8 in total here. So that will be the electron configuration for oxygen, okay? So with that being said, as we're reading through, they also mentioned noble gas notation. For this, we don't really need to do that. The noble gas notation, though, is simply, to save you some time, because sometimes you get really far, like selenium or bromine. You get further and further in the periodic table. The noble gas notation is where you take your most recent noble gas. In this case, for oxygen, it will be helium. And then you continue from the next row. So then I'm starting now with 2s2 2p4. This is a noble gas notation because this is pretty much saying that it has everything that helium has, and now we're focusing on what it should have theoretically on its valence electron, like this outer shell. You notice that we could have picked anything, like if we're doing like selenium, which is on row 4, for example, you would notice that we would use argon to say represent that, oh yeah, it has everything, before it has everything that makes argon, and then you'd be adding the parts that come after it. So you'd be like 4s2 and so on. So with that being said, though, let's see. Oxygen, exactly. Chemical elements with atomic number of 8, 1s2, 2s2, 2p4. Perfect. As you can see, here is their noble gas notation as well. It's He2s2, 2p4. So, with that, let's move on to question number 3. What is a molar mass of H3PO4? So, for these, the important thing to understand about getting the molar mass is that you want to be adding the constituents of its atomic mass to be able to get that. Just as a little side note, when you look at the name, well, the molecule H3PO4, it's good, not for this question, but it's always good to just recognize what that compound is. So right now we have 3 hydrogens, okay? In fact, we would actually ignore hydrogens for now and focus on this end. So PO4, okay? PO4, this is a phosphate ion, okay? That is something that unfortunately you kind of have to memorize, just because, especially with a lot of the 8s, like phosphate, nitrate, sulfate, these things you kind of have to recognize what they look like. And the key thing is that actually that because there's 3 hydrogens attached to it, we know that the phosphate ion is 3 minus. Okay, so this is composed of a phosphate ion and 3 hydrogens. So the cool thing about this is that when you start recognizing, you'll see that when a hydrogen is kind of just thrown in there, even if in this case it's 3, like when you have a main component and you see that hydrogens are kind of just thrown in, you formed an acid. Okay, in this case, the phosphate drops the 8 and instead ends with the ic acid. So you will have phosphoric acid. That is what H3PO4 is. It's important to note this just because if the question asks what is a molar mass of phosphoric acid, this is a good way to approach it as well, to where it's now you're saying, okay, even though I don't have that molecular formula, I still recognize what phosphoric acid would be as, you know, its molecular formula. With that being said, let's now calculate its constituents. So we have 3 hydrogens, okay, 1 phosphate, sorry, well technically yes, 1 phosphate, but 1 phosphorus and 4 oxygens, okay? And with that being said, that means 3 times hydrogen, so you want to multiply that actually by its atomic mass units. Well, atomic mass. And that would be right here. You see this number where it says the weight? That is the number we're going to use, 1.008. Okay, that's for hydrogen. For phosphorus, its weight, you see that number at the bottom? That's 30.974. And oxygen, 15.999. So now we'll do the multiplication, and 3 times 1.008 is 3.024. Okay, I believe at least. Always good to double check with the calculator if you have the opportunity. Yep. And phosphorus is 30.974, and oxygen should be 63.996. Double checking as well. Yep, alright. And then now that we have the individual components, you would add them all up together because that's just your total. So we have this plus 30.974 plus 3.024, and we get the molar mass is going to be 97.994. And the important thing here, don't forget your units, this would be grams per mole, because now you're saying that per mole, so for every 1 mole of H3PO4 phosphoric acid, you should have 97.994 grams of that molecule. Okay, so let's see how we did here in regards to that. All right, they're talking about the different properties of phosphoric acid and what interactions and exactly what solutions, what formulas it's involved in. And here now they're now talking about the molar mass, and here they have it for us, 97.994. They do go ahead and discuss other aspects of it, like the density, melting point, boiling point, which is all good information too. The cool thing is that when you're doing like your chemistry lab preps, for some of you, they do ask you in terms of you know, let's see, like you want to familiarize yourself with the materials you're using. You can actually find this information as well if you like search up like the not the WMIS, but it usually comes along with the WMIS, the Workplace Hazards Materials Information Sheets, but it goes into further details about the certain chemicals that you're using, where it does list you like molar mass, melting point, boiling point, and other important things such as how to store it and what happens if, you know, you get some on you, you know, and just things like that. Nothing depending on the concentration, it's usually nothing serious, but it's just important, and it's stressing things like, making sure that you rinse thoroughly, just because these are chemicals that you are dealing with, so they want to make sure that you're handling them properly. So if you're ever confused, that is something that you can always kind of search up to get actually like a good amount of chemical properties of that molecule. So with that being said, we have now the molar mass of phosphoric acid. So let's move on now to question number 4. What is the formal charge of chlorine in the molecules Cl2, BeCl2, and ClF5? So formal charge of chlorine in molecules Cl2, BeCl2, and ClF5. So the key part here is that they're asking for formal charge and not like your oxidation number and things like that. To find formal charge, you first have to be able to draw out its Lewis structure, its Lewis dot structure, just because you want to be able to see how these things are bonded to each other in order to actually assign that formal charge. Okay, you want to see the distribution of electrons between each one. So with that being said, to draw the Lewis structure, we're actually going to make sure that we get the right amount of electrons for chlorine. So chlorine is on the 17th column, okay? And for those that are in the 17th column, typically have 7 electrons to work with. You can also show this of its valence shell by the electron configuration. So for chlorine, if I want to do the shorthanded notation, which is like the noble gas notation, I would start at the element, the noble gas that comes prior to it. Okay, so that would be neon, right? And then when I go through the periodic table, I will start with my S subshell, so that's sodium and magnesium. That would make up 3s2, and then I jump all the way to the columns 13 through 17 to where chlorine is, and that would be 3p1, 2, 3 for phosphorus, 4 for sulfur, and 5 for chlorine. So 3p5. Okay, and you notice that we have 2 and 5 in our most outer, because everything that comes up to neon would be in your first and second shell. So this would be the third shell, the most valence shell, and you notice that here it also shows that in total it has 7 electrons it's working with. So this Cl2 here will be working with 14 electrons total. BeCl2, so that would be beryllium. As you can see, beryllium is actually the second element on the second row. So if we were to start with that noble gas notation as well, beryllium, okay, would start with helium, and then it'd just be 2s2. That's all there is. And then you can see here, beryllium only has 2 electrons it's working with. So we have Cl2, which is 14 plus 2. In total, we're working with 16 here. 16 electrons for the BeCl2. And then ClF5, fluorine, okay? If we did the noble gas notation as well, it's actually still in the same row as beryllium. It just extends further. So it would encompass that 2s2 for the lithium and beryllium. And now we're in the P subshell, similar to the chlorine, but it's right above it. So it'll be 2p1, 2, 3 for nitrogen, 4 for oxygen, and 5 for fluorine. So it'll be 2p5. All right. So with that being said, we can see here that fluorine actually does also work with 7. So in total, we have 7 times 5 plus 7, which is also 7 times 6. So we're working with 42 electrons here. Okay, so let's start with Cl2. We're working with 14 electrons. So I have chlorine. I'm just going to start with just one single bond between chlorine. Single bond means that each chlorine right now is sharing one of its 7 electrons. So let's fill up the rest of the shell with the corresponding electrons. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay, and you notice right away actually this satisfies this octet rule. And if you counted, you'd see actually we have 14 electrons because we have 2, 4, 6 right here on one side of the chlorine, then 8 would be in the middle, then 10, 12, 14. So this is perfect. Now let's find the formal charge. The equation for the formal charge is the amount of electrons it can work with, which would be 7 for chlorine specifically. That's what they're asking for. And this can be applied to any of them actually, like the beryllium and the fluorine. But in this case, they're asking for the chlorine involved in these molecules. So there's 7, and then we're going to subtract how many electrons it actually has, both the ones that it has by itself and the one that it's sharing. So the one that it has by itself here for either chlorine is going to be 6, okay? And the one that is sharing is going to be 2. But because it's sharing, you have to divide by 2. So it'll be 6 plus 2 divided by 2. So when you have 7 minus this, you're in a sense doing 7 minus 7, because 2 divided by 2 would be 1, so 6 plus 1 is 7. So the formal charge here would be 0. So the chlorine in these, like the diatomic molecule or 2 chlorines, that has a formal charge on each chlorine of 0. Now for BeCl2, let's draw it out. So we're going to have beryllium in the middle because it's the only unique one, and also it has relatively the most space to actually form bonds since it's working with 2 electrons. So the same thing here, we put the chlorines on the side. Okay, right now each chlorine is still sharing 1 of its 7, so 2, 3, 4, 5, 6, 7. Same here on this side, 2, 3, 4, 5, 6, 7. And beryllium in this case is already using up 2 of its 2 electrons it can actually share. So beryllium is already done. So if we added all this to make sure that we do have 16, it would be 8 on one chlorine, 8 on the other chlorine, and that is what we'd have. So now to find the theoretical charge, sorry, just have to find the word, there we go, formal charge of chlorine. In this case, we still start with 7, and you notice that it's really almost the same thing as above, because each chlorine has to share 2 of its electrons, but this time it's not with each other but with beryllium. So it'll be 6 plus 2 over 2, and the formal charge of this will also be 0. Okay, and now ClF5. So for this one's a little bit trickier. Well, I guess it's just more extensive. So we have the chlorine in the middle because that's the unique one in this case, and it's surrounded by 5 fluorines. And you're probably wondering, how is chlorine going to do that? And the simple answer is that chlorine can do that just because it can, which is really annoying sometimes. But there are certain things called like the octet rule. But at the same time, the octet rule kind of gets thrown out the window when you're dealing with molecules such as these. It just decides that, you know what, I think I'm just going to do whatever I want anyways, and it's your job to memorize what I look like. So with that being said, what's going to happen here is that we have ClF5, so it's going to be that the fluorines are each going to be attached to the central chlorine, and it's going to be sticking out like that as well. That's the 5th one. And then we have to make sure we add every valence electron. So fluorine right now, each fluorine is sharing 1 of its 7 with chlorine. So it's going to be 2, 3, 4, 5, 6, 7. Same thing here. 3, 4, 5, 6, 7. Okay, same thing here. 2, 3, 4, 5, 6, 7. Same thing here. 2, 3, 4, 5. Oops. Yeah. Whoopsie. 5, 6, 7. And I only put this one in red just because we can see that it's the one that's really breaking the octet rule. Okay, 6, 7. All right. So I hope you can kind of visualize that. Maybe I should have drawn it a little bit bigger. But now chlorine, as you may have noticed, is only sharing so far 5 of the 7 electrons it can actually work with. So not only does it have that extra fluorine breaking the octet rule, but chlorine actually also has a lone pair. So yes, chlorine is quite an extensive molecule. I mean, not atom in this case that's working overtime in this molecule. But let's actually now see what the formal charge for this would be. So same thing, we start with 7. All right, and we're looking specifically at chlorine. So chlorine right now, okay, only has 2 electrons to itself, that lone pair down there, okay, and it's sharing 2, 4, 6, 8, 10 electrons. So coincidentally, actually, we still just get 2 plus 5, and it actually works because 7 minus 7 is still 0. So all these chlorines had a formal charge of 0. And if you're skeptical in terms of the amount of electrons we had, and if it was actually correct, we have 8 on each fluorine, 3, 4, 5, so that's 40, considering the fluorine and the chlorine are sharing 2 of those 8. But that's 40 in total, plus the 2 extra electrons chlorine has as a lone pair. That's 42. So we actually did get all the electrons on this Lewis dot diagram. So with all that being said, the formal charge, as we've shown for all these, for chlorine is actually going to be 0. And exactly, talk about the equation. So 7, 6, 2 over 2, 2 over 2 again, and then this one, as we discussed, it was 7 minus 2 plus 10 over 2. So yes, these are some of the questions you can get. It kind of appears as almost a trick question because why am I getting the same answer over and over again? But actually, the reason being is because, especially when it comes to formal charge, the goal of the atom presented in the molecule is to orient itself in a way to where its formal charge can be as close to 0 as possible, because that is when it's most stable. Okay, so getting a formal charge of 0 is something that you should actually be hoping to expect, especially when your actual molecule itself has no charge of its own. If you're not working with an ion, then you most likely should not have like a formal charge of like 1 or 2 or -1 in there. You could, but then that means you should be looking for, if you have like a -1, for example, one of the formal charges there has to be a +1 for you to still have a neutral, a non-ionic molecule to where it has a charge, because you want them to cancel out. So let's move on to question 5. How many valence electrons are in zinc? So, valence electrons in zinc. To be able to find this answer, actually, we actually need to use our electron configuration, especially because zinc is a transition metal. It's hard to just see it and be like, okay, well, zinc then has, exactly, what does it mean for zinc to be in the 12th column? What does that mean for electrons? This is why I do stress that if you're ever unsure, it does, no matter where you are in the periodic table, if you know how to do your electron configuration, that's usually the best approach to figure out how many valence electrons you're working with typically, especially when you're dealing with transition metals. The alkali and alkaline earth metals, those ones can kind of be seen as face value, and also between columns 13 through 18, those ones you can kind of assume what their valence electrons will be. But for transition metals, this is when we just do our check through our electron configuration. So with that being said, let's make sure we write our subshells in properly. We have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, and it keeps going, but this is as far as I'll go, just because we are trying to get to zinc. Okay, so zinc, right, is the 30th element on a periodic table. So let's actually, what I like to do, especially if you're having a hard time with electron configuration, the goal is to count through. The S subshell can only fit 2 electrons, okay? So that'll be the first and second, I guess, elements in your row of that periodic table. In this case, it would be hydrogen and helium. That'll be 1 and 2. So right now we have this completed, and we have at least one S2, okay? And then we follow that trend. Lithium and beryllium would be what compose that 2s section, and we completely go past that because we're aiming to get all the way to 30, okay? So 2s2 is complete. And then from boron to neon, that would be your P subshell, and you notice that there's 6 elements in that span. So we'd count through P, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 for the neon. So these now we know we have 2p6, and we keep going forward, okay? We're in the third third row right now. So now we've gone past that into the 3s, so that's 3s2. And then we have aluminum through argon, that would be the 3p6. And now we've passed that. And now here we have, okay, 4, where do we got? Just make sure, yep, 4s2, potassium and calcium, okay? So we've gone past that. But now we're actually going all the way towards zinc. Now we've entered, as you can see here, based on these arrows, we're entering our D subshell, okay? And the D subshell works a little bit different if you noticed. Instead of it being that we say 4D, this subshell here on the 4th row actually starts with whatever row you have minus 1. So it would be 3D actually, okay? So in a sense, think of it being actually in the orbital prior. So we have from scandium all the way to zinc, and if you count, that's 10. So that's 3D10, okay? And now what I like to do is rearrange it based on the numbers that come first in front of it. So it's 1s2, 2s2, 2p6, 3s2, 3p6, whoops, almost did it again, 3d10, 4s2. It just allows for a better visualization. And you can actually check that you actually ended up on the 30th element by adding up all these superscripts. So 2, 2, 6, 2, 6, 10, 2. So let's see what happens when we do that. 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2. And it does indeed equal 30. So this actually would be the electron configuration for zinc. So now it's asking for its valence electrons. As I said, we have now from 1 to 3, that would be your shell prior, because the 4th is now the biggest numbers. That'll be your most outer shell. So with that being said, we only count this as your valence orbital, okay? And to find out how many electrons, we look at the superscript there, okay? And that's 2. So for this question, the valence electrons in zinc actually would just be 2 valence electrons, because that would be what is available from that most outer orbital, okay? So that would be the valence electron for zinc. Just to be able to write this easier, because as you notice, if you get further and further down the periodic table, it can get quite extensive. So what I also like to do is that if we look at the most previous noble gas, which is argon. Okay, we can start from there, and you notice that we now just hop right into our 4s2 and the 3d10. And as I said, I like to just make sure that the 3 comes before the 4, so it'll be 3d10 4s2, and this is actually the same thing as that. Okay, it's just a noble gas short-handed configuration. And I just do this as well because it does allow me to have an easier time visualizing my outer shell. Although we still have the 3 here, the important thing is that we recognize that this 4 is going to be in the shell that comes after. Okay, so yes, 2 valence electrons. As you can see here, they did that as well. They actually provided both the short-handed and the long notation. And the goal here, the final energy level, 4s2, dictates that the number of valence electrons in this case is 2 electrons. So this is correct. So now we move on to question 6. All right. Is granite a heterogeneous mixture? Okay, so the first thing we have to understand is, what does it mean to be a heterogeneous mixture, and what does that mean relative as well to a homogeneous mixture? In fact, what is a mixture? Okay, so a mixture is it's a little bit tricky here. The best way to explain a mixture is a bunch of compounds slash elements held together by intermolecular, not intra, so not your bonds, but just like kind of like the pull they have with each other, intermolecular forces. These forces are like dipole-dipole, dipole-ion, or ion-dipole, same difference. Or like, to go further, like hydrogen bonding, trying to think here, or like van der Waals forces, which is kind of like your pseudo-gravitational force that every molecule kind of has. But those are just different types of intermolecular forces. And the key thing here is that it has to be different compounds slash elements held together by that. The reason why I say that is because, for example, having a glass of water, that, okay, is all H2O. That would just still be considered a compound, or lots of that compound, because, I mean, as long as your water is pure, which is what we're assuming, there's no different compound in there. It's all H2O. Now, if we were to compare that with air, for example, which has water vapor, oxygen, nitrogen, and all these other gases floating about, that is a better example actually of a mixture, because these things are all just kind of floating there, and they're also interacting with each other through intermolecular forces as well. That would be in terms of why they kind of, like, I guess, are near each other and they are bumping into each other and moving about and stuff. That would be the role that intermolecular forces play. Okay? The reason why I mentioned that is because there are some mixtures like air to where it's kind of more free roaming, and there's other mixtures like, I'm trying to think of a good example. Copper, nope, that's an element. There was a good example I could have. Bronze, for example, is a mixture, okay, where you kind of just melt, I think it's copper and tin or something like that. But exactly, like, you mix those two elements, and they are held by those, I guess, intermolecular, like, metallic bonds and forces, and that is considered a mixture in itself, and that's how it's held together, because it's not really bonded to each other per se. It kind of creates like a lattice, no, not really a lattice, but more so like the way the atoms are spread out with each other, they're not held together by bonds, if that makes sense. It's not intramolecular forces that holds things like copper and tin together to form that bronze. So in this question though, is specifically talking about granite. So granite, okay, I'm going to tell you right now, especially when it comes to a lot of rocks, they're a combination of different minerals, which is already a big hint. Different minerals, and for it to be a different mineral means it has to be a different compound. So we know for sure that granite is, that granite is a mixture. So yes, granite is a mixture because exactly we're dealing with different compounds, different minerals, and different things in that rock. Now, homogeneous versus heterogeneous, okay, that's what we're going to discuss next. Homogeneous, okay, that type of mixture is when everything looks the same, which is why I kind of brought up the bronze. If you look at it, well, I mean, if you have a really pure like bronze sheet, everything looks bronze. Everything looks like it's equally distributed throughout, even if you may not be able to see it. Like if you look as close as you can, it just looks like everything is in uniform construction. Okay, everything is like you can't really tell which part of bronze is tin and which part of it is copper, if that makes sense. You just see it as one uniform thing. Okay, that would be an example of a homogeneous mixture. Okay, and a heterogeneous mixture would be one exactly kind of like granite, to where you can actually see the different parts of it, the different minerals, whether it's through coloring and such, where it's like, okay, as they show a picture of granite here, you can see it that there's definitely different parts mixed in, and you can see the different phases and different parts in this material. So that would be what heterogeneous is. So homogeneous is uniform and can't see different phases, and heterogeneous is non-uniform, can see different phases. So with all that being said, then granite would be a heterogeneous mixture. So yes, heterogeneous mixture, that is what granite would be. So as you can see here, we kind of just first discuss what a mixture is, and then we discuss homogeneous versus heterogeneous, and that's how we're able to say that yes, granite is a heterogeneous mixture. Okay. And now, let's move on now to question number 7. So, this one's asking us a pH of 6 is how many times more acidic than pH of 9. Okay, so this is gonna be well, sorry about that. So exactly, so for this question here, the way we approach it is that we need to know our formula, which is given to us there, but this is one of the formulas I do recommend memorizing because it does come up often when dealing with acids and bases. So we have pH is equal to negative log of hydronium. Okay, so when this type of question is asking how many times more acidic, it's trying to ask you how many times more of this stuff does it have compared to that, because it's not asking you what the pH difference is, because then you just say, oh, it's 3 times more acidic, and that would actually be incorrect. The goal here actually would be to now flip this equation over to where now you're solving for that H3O. And if you remember your logarithmic rules, the way you do that is, it'll be, just to make sure I understand, You move the negative over there, so it'll be negative pH is equal to log of H3O, okay? And then we know that this is going to be the base 10. So in order to now get rid of that, you have to now put everything to the power of 10, but make sure you put it in the right spot. So it'd be 10 to the power of all this, and then this would cancel out. So then now we're left with, well, if we switch it over, just make it more sense, the concentration of H3O, aka how many times more acidic, is equal to 10 to the power of negative pH. Okay, so now that we do that, we're actually going to see now how much more one pH is than the other, because once we find out the pH of 6, what it translates to the H3O, we find that out for the pH of 9, and then we divide 6 over 9 to see how many times more does it actually, you know, overcome it. So let's see here, 10 to the power of, 10 to the power of negative 6. We have a very small 0.000000001. Hopefully I counted that right. 3, 4, 5, 6. Yep. So that's 10 to the negative 6. Put to that. And 10 to the negative 9 is equal to 0.000000009. Well, 1. Because you should have 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So then now we divide this 6 by the 9 to find out how much 6 is stronger than 9. So we have the 1 times 10 to the negative 6 divided by 1 times 10 to the negative 9, and you will see that you should get an answer of 1,000. Okay, so at first glance you would think that, oh, it's just like maybe 3 times or something, but remember that because we're dealing in the exponential and logarithmic scale, each, I guess, increment by 1 on the pH is a change by 10 times. And because we changed 3 levels, that's how we're able to go from 10 to 100 to 1,000 times more acidic. So this pH of 6 is 1,000 times more acidic than the pH of 9. Okay? And you can see here exactly, they flipped the formula over, which is what we got. And then they got these two values. And when you divide them together, that's the ratio you get. So this is correct. So now we move on to question 8. For this question we have, what is a molecular formula for butane? Okay. For butane, C4H10. So funny enough, actually, as the answer also states, the answer is actually given to you right here. This is the molecular formula for butane. Now, to be able to get there, though, that's the part you have to understand. When you're naming hydrocarbons, okay, you have to recognize how they, I guess, each prefix indicates how many carbons you have, okay? So we're going to just go through a quick sheet. We have, for the hydrocarbons, it's meth, which translates to 1, eth, which translates to 2, pro, which translates to 3, or prop, bute, which translates to 4, 5, pent, which translates to 5, hex, which translates to 6, hept, which translates to 7, oct, which translates to 8, non, which translates to 9, and dec, which translates to 10. So these are all you have in terms of the prefix. Now, in regards to the suffix, okay, this is where it gets a little bit trickier, but and when they're just asking for molecular formula, they just want you to be able to, you know, do the correct math. So when it ends with an ane, okay, the amount of hydrogens you have is whatever number you see like here in terms of like what you've identified as the amount of carbons, and you have to do 2n plus 2 that amount. So if we wrote down our formula of CnH, it would be H2n plus 2 when it comes to things that end with A and E as its suffix. So with that being said, as you can see when we plug it in, butane, based on this chart here, is 4. So 4 carbons. So then the amount of hydrogens will be 2 times 4, which is 8, plus 2, which is 10. And that is how they got this. Now in this question they asked if they were asking for the empirical formula. The empirical formula, that one's a little bit trickier. The concept there is that if they said, okay, this formula by moles is composed of this percentage of carbon and this percentage of hydrogen, that would be how you would use those values to be able to find the empirical formula, because the difference between empirical and the actual molecular formula is the empirical formula does not factor what the actual molar mass is. It just gives you your lowest multiple constituents of it. So you see how butane is C4H10? The empirical formula would be that, I guess the lowest common, taking out the greatest common multiple in 4 and 10. In this case, it will be 2. So that's how they ended up with C2H5. Because if you're doing like the whole percentages, the percentages won't tell you like how many of each carbons you actually have. It just tells you how many carbons you have based on how many hydrogens you have. And they usually work with whole numbers. That's why this is our lowest, I guess, ratio, if that makes more sense. So we actually have, for every 2 carbons, there's 5 hydrogens. We don't know how many carbons they are. We just know that for every 2 carbons, there's 5 hydrogens, okay? So exactly, the simplest ratio formula. But that would be for like the empirical formula. Here, it was asking for a molecular formula. And although it did give us the answer, the important thing is to memorize this chart here, okay? And this equation here to also find out how many hydrogens you have. All right, so let's now move on to question 9. This is correct. They were wrong in saying that you got the answer. So, number 9. Several Lewis structures can be written for per bromate ion, BrO4 minus, has many Lewis structures. The central Br with all single BrO bonds, or with 1, 2, or 3 BrO double bonds. Draw Lewis structures of these possible resonance structures and use formal charges to predict which makes the greatest contribution to the resonance hybrid. Okay. So with that being said, I'm just going to say draw Lewis structures and then use formal charges to see which makes greatest, to see which is most stable. The reason why I say like this is because as we were discussing with formal charges, but specifically to this question here, the formal charges, right, you want it to be as close as you can to everything being 0. That is a goal for formal charges. If there's a way, if you see like there's one that's like +1 and the other one's like -1, the goal of the, I guess, the molecule is to rearrange itself to where actually it would just be 0 throughout, instead of it having a positive end and a negative end, if it's possible to rearrange itself. That's why formal charge is help find out the stability, because you'll notice that the most stable one is the one that has the least amount of, I guess, positive and negative charges. It just has the most amount of like 0 charges. So with that being said, let's draw these Lewis dot structures based on these instructions. So we have bromine, okay, and they said a single bond on each one at first. Okay, so with that being said, though, I guess a pretty good place to start would to figure out how many electrons each is actually donating. So if you look at the periodic table, we have bromine being on the 17th column. Okay, so it's going to donate 7 electrons. Oops, that's boron. Bromine is with an R. Okay, and oxygen is on the 16th column, so that means it's going to donate 6 electrons, and because there's a minus, it's going to be plus 1 more because electrons are negative. So it's going to be 6 times 4 because there's 4 oxygens, plus 7 plus 1. So we need to account for 38 electrons total. So 38 total. Okay. So now let's draw the oxygens. We have oxygen here, oxygen here, oxygen here, oxygen here. Okay. And now, of the 1 electron oxygen is sharing, there still needs to be 5 other ones included because of the fact that oxygen is trying to think about this. Because of the fact that oxygen is only sharing 1, so we label it like this: 1, 2, 3, 4, 5. In fact, I'll just say it a little differently. We start with 1 already with the sharing with the bromine, so it's 2, 3, 4, 5, 6. Same thing here: 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And now we have that extra electron. Okay, let's just add it here on this oxygen. So bromine, though, is only sharing so far 4 of its 7. Okay, so as you notice, it's sharing 4 of its 7, but the oxygens on the outer shell all are quite incomplete, and bromine has already filled its octet rule. So being the generous person that it is actually going to just let these oxygens hold on to the other 3 left for bromine, because exactly it's shared 4 of its 7. That is one resonance structure that they mention. Second resonance structure is one where bromine has 1 double bond, and then there won't be 2 double bonds, and then the last one will be 3 double bonds. So the first iteration, 1 double bond. So we're going to signify that by just like that. Oxygen here. The rest are single bonds. And the same thing where it's 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And the oxygen up here actually is sharing 2 already of its 6. So 3, 4, 5, 6. So I'll just move this one over here, because now this oxygen has completed its octet rule. It's all set to go. And now let's see actually if we've accounted for every electron, the 38. So just in the previous question, I don't think I counted them. We had on each oxygen is 8, so 8, 8, 8, 8. So just to make sure, bromine 6 times 4. Yep. Oh, whoa. It's not 38. It's 7 plus 1. I don't know how I did 7 plus 7. 32. Oof, that makes more sense. So 32. Sorry about that. So in the calculator, I accidentally added another 7 instead of a 1. So we actually have 32 electrons to fill up. And as you can see here, this satisfies that. This bromine here is not quite done. Right now it's sharing 5 of its 7. So remember, we still have that 1 extra negative. and then still sharing now 5 or 7, so it's generous enough to now give these other 2 oxygens a nice 2 electrons. So with that being said, let's move on now to the next bromine iteration. The next bromine iteration would be still bromine in the middle, but now it has 2 double bonds. Okay, so one here, oxygen, gonna look like the other one. This is gonna look like that one as well. Then we have these 2 oxygens that still are stingy on trying to share a bond. Oops, did too many. As we said, there's still just 1 extra, and then bromine is just going to give up 1 of them because right now, so far, it's sharing 6 of its 7. So it's just going to give that oxygen the last one. So that is going to be the 3rd iteration. So far, we're doing good. We're doing good. Okay. And now for the 4th iteration, we have with 3 bromine double bonds. Okay. So it's going to be bromine, double bond here, double bond here, double bond here, and 1 oxygen by itself. Oops. 1 non-double bond oxygen. And then we do the same thing, oxygen sharing 2 of its 6. So 3, 4, 5, 6. Same as the rest, 3, 4, 5, 6. 3, 4, 5, 6. And there, because it's going to be 2, 3, 4, 5, 6. And then that extra electron is going to now join the oxygen over there. So that's what we have now for this one with 3 double bonds. So now let's go in to use the formal charges to figure out what's going on. So let's start here. The bromine formal charge here. To find formal charge, the equation is what electrons it can typically bring. So I guess n will be the number of electrons, and you subtract that from the number of electrons by itself. Okay, plus electrons shared over 2. That is a formula. I'm going to use that. So bromine brings 7 to the table, and right now in this it has no electrons by itself, and it's sharing 8. So in this case here, bromine, that's 7 minus 4, is going to be 3. Alright, so it has a plus charge of 3 as a formal charge. Alright, and remember that we want to have a total of -1 here for each one, because BrO4, as they stated, is an ion with a negative charge, an anion. So that means these 4 oxygens, hopefully I have to make sure that they cancel out the +3 and even make sure that it goes beyond that. So the oxygen here, actually, this is for every oxygen there. It brings 6 to the table, but it actually, as you can see, already has 6 to itself, 6 electrons, and it's sharing 2 with the bromine each time. So 2 over 2. So each oxygen actually here is -1. As we discussed earlier, this already I can say is not as stable as they wanted. Look at how it's distributed to where bromine is literally being such a positive number and there's all negative numbers surrounding it. There has to be a way to rearrange it to where we actually get some more neutral pieces. And you will see that actually as we move on. So bromine in this case now has a double bond, meaning that now it still has 0 electrons by itself, but it's sharing, okay, instead of 8 from before, it's sharing 4, 6, 8, 10. Okay, so now bromine has a charge of 2. Okay, so now it's 2 plus. Alright, which means we're actually kind of getting closer, because with that, all we need now is 3 minus to get rid of this. And the oxygens, okay, down here, so like these 3, those ones would be still the same. 6 minus 7, whoops, 6 minus 6 plus 2 over 2. That would still be minus 1. So that here would be minus 1, minus 1, minus 1. But the oxygen at the top, actually, as you notice, is actually going to be, it right now has only 4, and it's sharing 4. So this one actually equals 0. So this one, oxygen here is fine. And now we have 2 of them doing the same thing in the next, I guess, resonance structure over. We have 6 minus 4 plus 4 over 2, which is still 0. And that's happening to 2 of them now. And the bromine in this case, so I mean, the other 2 though is still going through the same thing of 6 plus 2 over 2, which is minus 1. So that means these 2 here, minus 1 and minus 1 there. And the bromine this time would be 7. Okay, minus 0 because it doesn't have any by itself still. But now it's actually sharing 12. And with that, it's only plus 1. So we're getting actually quite close. So you probably already guessed the hint that now with this bromine, that yes, it broke the octet rule, but it actually prefers this simply because of the fact that how do I do this? There we go. Because of we want to be able to make sure that, let's see here, as we go through, bromine in this case is 7 minus 0 plus 12 over 2. Okay, oops, not 12, sorry about that. Now if you counted it, it's 4, 8, 12, 14. And now we finally get bromine to be 0. Awesome. And there's only one oxygen, because the rest of the oxygens are still now with the double bonds, they're doing this. 4 over 2 equals 0. There's only one oxygen here, where it's 6 minus 6 plus 2 over 2, which equals to minus 1. Only one oxygen does that, which is right here. Okay, so when we talk about resonance structures, okay, the one that's going to be contributing the greatest to the resonance hybrid would be the last one. Why? The one with 3 double bonds. The reason being is because that actually is the most stable one when it comes to the formal charges. There's no where it's like cancel out within the same molecule. It's done it in a way to everything else is neutral, and there's literally only one negative charge, which is actually what it translates to. Instead of it being to where I have like 5 positives and 6 negatives and I get 1 negative in total, what I've done effectively here is said I'm going to rearrange it so that everything else is satisfied, and that way I meet my minimum requirements to have that minus 1 charge. So this would be the most stable. Okay, and as you can see here, they did draw that. So, and they did number it 1, 2, 3, and 4. So as I said, 4 would be the most stable. And as they go through, they explain the first structure. Exactly, they have a 3 plus and all these 1 minus 1s 4 times. And the second structure is a little bit less, and it keeps going. And then the fourth structure. So the lowest structure that gives the greatest contribution, as I mentioned, would be the fourth structure. Okay, so now let's go on to question 10. Okay, so we have, what is a Ka for a strong acid like HCl? So for this question, actually, the answer is in the question. Well, it gives you a big hint of what we're dealing with. HCl is a strong acid. I'm going to actually underline and highlight it, because that right there actually tells you what your Ka is. These are things that you do have to memorize, but anything that's labeled as a strong acid means that it has a Ka is greater than 1 for strong acids. So with that being said, weak acids in the opposite end are where they're less than 1 but greater than 0. Why do we say this? That's because when it comes to strong acids, you can actually search up like an actual empirical theoretical number for its Ka, but once you have a Ka greater than 1, you are saying that it dissociates completely in a solution. As in, when you pour in some hydrochloric acid, you will not see HCl still floating in there in the aqueous solution. You actually see just the hydronium and the chloride ions. They have completely separated and done their part, and that's why it's frankly quite acidic, because of the fact that it's pretty much able to maximize all the hydrogens it has on the chlorine to make sure it produces the most amount of acid it can produce. So with all that being said, the reason why I mention this is because once you pass the Ka of 1, your Ka value becomes almost irrelevant, as you don't need to know what the Ka value is to be able to further solve questions of, like, you know, what's the pH of this amount of HCl. Like if I had a 0.5 concentration of HCl, okay, with the formula using pH equals to negative log of H3O, because we had 0.5 of HCl and we know it dissociates completely, we already know then that we have 0.5 of H3O. We don't need to use a Ka in order to solve it. Like so Ka is equal to is equal to products over reactants. So it'd be like H3O plus the conjugate base. In this case for HCl, it would be the Cl minus over the conjugate acid, the HA, which would be the HCl. But exactly, we don't need to use this because this formula here is typically used to find the concentration of the hydronium, so we can actually find our acid. But if we can just see from the fact that it's a strong acid that dissociates 1 to 1, we don't need to mess with the Ka formula actually, and, you know, solve with like quadratic equations and stuff. We can just simply say that the pH is going to be represented by a full dissociation from of the acid from the chloride ions. So all that is pretty much saying is that for this question here, the Ka for a strong acid, you are allowed to just answer it's greater than 1, because you don't need an actual value. Once you've said it's greater than 1, that's all the information you need to be able to solve questions when it comes to finding out the pH of strong acids. Okay? So in this one, they gave a theoretical number here. So what's happened here is that, as I said, the numerator is very large compared to the denominator. So in this case, for example, if we had 0.5 dissociate, so we have 0.5 over 0.5 over almost 0, because in a sense what's happened here is that, sorry, I phrased that wrong. It would be 0.5, because that's how much dissociates if we had 0.5 moles of HCl, and this would be like almost 0, because what's happened here is that it completely dissociates. We have almost literally nothing left of it, which is why you can get such a monumental number of Ka, which is why we cannot use this, I guess, formula to try to solve for it, because you're almost divided by 0. And then that's why, exactly, once K is greater than 1, you can't really work with it anymore. So with all that being said though, exactly, I keep the answer because I think they're trying to ask for the relationship here, that a Ka for strong acids is greater than 1, and leave it at that. You are free to search up theoretical values as well if you want to further understand it, but you'll see that when it comes to strong acids, whichever strong acid you're searching up for, that Ka value will be monumentally bigger than 1. Alright, so now time for just a quick drink of water as we move on to question 11. Okay. So, we have for question 11 here. All right. Ammonia NH3 is a weak base with a Kb value of 1.8 times 10 to the negative 5. Okay. So let's just write it down. Ammonia is a weak base with Kb of 1.8 times 10 to the negative 5. What is a pH? And percent ionization. So for this, we actually need to go through step by step to be able to find this and use certain things to be able to put the whole picture together. The first thing we need to understand about ammonia is how it actually reacts with water to be the weak base as it says it is in this question. Okay, so we actually write down our equation. That would be NH3, an aqueous solution or gas, but most likely aqueous solution to actually mix with the water, plus H2O, liquid, turns into NH4 plus aqueous plus OH minus. So here you should be able to see that one of the hydrogens from the H2O moved and attached instead to the nitrogen, or the ammonia instead. So with that being said, okay, our formula that we're going to use in regards to Ka, well Kb actually, because we're dealing with the OH, so we're actually going to use Kb, but it's actually very similar to Ka, but it just says Kb is still products over reactants, but you have to make sure that you're solving for the concentration of hydroxide ions, and that would be the key difference there. So Kb is products over reactants, and we still do not count water because water is just the solution it's in. Okay, it's just like the liquid component. It's not factored in here. Think of it like almost like being an excess. Actually, even better. Yeah, actually, excess would be a good way to put it, to where it's just not considered because it does interact. It is part of the reaction, but it just like what the NH3 is submerged in. Okay, so that's the first formula we need. And in order to solve through this, we actually need our oh wait, we can actually solve for the percent ionization first, actually, because the way the percent ionization works is that it's by, I'm trying to remember, because the percent ionization is used to find the Kb. So exactly, it would be, yep, okay. It would be pretty much how much of the NH3 actually separated to the NH4 and OH minus. So we can actually kill two birds with one stone here, because we're going to use is the ice table. Okay, so with that being said, ice tables are initial change equilibrium, and we have to do this for each of the components that actually are factored in the Kb equation. So it's going to be the NH3, that's the OH minus, or actually let's start with the NH4 plus and OH minus. So the initial is that we actually put, think of it as we just put straight up just ammonia, okay? And as they said in this question, it's pH of 0.0390 moles. So we know we have this 0.390 moles in terms of the concentration. Okay, moles per liter. And that means because we put that there, we actually started with 0 for these two. So now for the change, we're saying that for every ammonia, it's going to produce, I guess for every mole of ammonia used up, it's going to use 1 mole of this, and it's going to produce 1 mole of the ammonium ions and the hydroxide ions. So that's why you just say minus x plus x plus x, okay? And the equilibrium is going to be now 0.390 minus x, and it's going to be just x and x. So now factoring that back into our KB equation, okay? We're going to get that KB is equal to, all right, x squared at the top over 0.390 minus x. Now, what we're going to do is a little bit of a shorthand. We're going to see if, in a sense, the concentration dwarfs the KB value so much to where you don't see a noticeable change in the 0.390 once it actually dissociates. So the way we do that actually is that we want to see if the concentration is at least 1,000 times bigger than our KB value. So we're just going to divide 0.390 divided by 1.8 times 10 to the negative 5. And wow, it is 21,000 times at least bigger than our KB. So with that being said, actually, our shorthand now, our formula just becomes like this. X squared over 0.390. Why? Because what we're saying here is that the change in the concentration of ammonia is going to be so small that we're almost going to round back up to 0.390. That's the assumption we make. So let's now actually do the math. We're going to multiply these two together, 0.390 times KB, and then we're going to square root it to be able to get x. All right. So that means now our x value is going to be, where is it? 0.390 times 1.8 to the power of negative 5, and then the square root of that. So our x value here is 2.65 times 10 to the negative 3. As you can see here, if I did 0.390 minus that, we get 0.387, which frankly isn't the biggest change ever comparatively. That's why. We could have solved this through like the quadratic equation as well, but you notice that the answer we would have gotten is going to be almost as close as well. So rather than just saving us the headache rather than having to go through all those steps. So with that being said, let me just check here in terms of what else we can do. Okay, so now we have our x. So we can actually use this to find our percent ionization. This is pretty much saying that of the concentration of 0.390, 0.265 times 10 to the negative 3 of it was ionized. So our percent, as in, was actually separated. So our percent ionization would be x over that 0.390. Okay, that's a total we have divided by so 0.23. Yep, divided by 0.390. Well, you should get our percent ionization times 100. So just add that. Okay, times 100, and we actually get it is a 0.679% ionization. And now that we've done that, let's use now the rest of the question to actually find out what our pH is. So the way pH will be found, we actually first find our pOH. Because what we've done here is find the concentration of OH minus. This will not give us our pH, but instead it will give us our pOH. But it's still the same formula of pOH is equal to negative log of hydroxide. Okay, so we're going to use that x value again of the 0.00264 etc. So we're going to now do negative log of that answer. And our POH, okay, when we put in the calculator, ends up being 2.577, around there. So to find pH, right, in this case, because 14 is equal to POH plus pH. So if we organize that, pH is equal to, just to make sure I have it correct, 14 minus POH. So 14 minus the answer we just got, the pH was going to be, for this question, 11.423. And so there you have it. We've now been able to give you the not just the percent ionization, but the pH as well. And just to be able to show you in terms of the whole quadratic situation, if we're to do the quadratic formula, I do have it memorized, just like how to approach it. The KB would be your B value. So what we have first, it would be the 1.8 times 10 to the negative 5 squared, okay, times 10 to the negative 5 squared, and it's going to be plus 4 times, or 1 times C. In this case, the C would be the 1.8 times 10 to the negative 5 times the concentration that were given to us, which was 0.390, okay? And then we square root that, okay? And then we would subtract that value from the KB. I mean, it would subtract KB from that value, so that would be minus 1.8 times 10 to the negative 5. Okay, and then we divide that by 2. So the answer I got when I did the quadratic equation, I got 0.264. So as you can see, making that assumption does work. 0.265 versus 0.264, and in fact the 0.265 I had to round up to get there. So the difference was literally like the number after. Like there was quite a very little difference of whether to use a quadratic or not. So with that being said, I'm pretty confident in my answer in terms of how we solved this. So as we go through, they did set up the ice table, and exactly they also dropped their x because it's so negligible, okay? And we showed that because we did the whole comparing if it was 1,000 times greater, the concentration versus the KB. And so the first thing they did was find the pH, which was indeed 11.42, and the percent ionization, okay, was the amount of hydroxide produced versus the total we were dealing with, not just the NH3, because technically the NH3 now is a little bit less, and exactly the percent ionization was 0.68, which is what I got. They just rounded a little bit different. So this is correct. And now question number 12. How many valence electrons does each of the following atoms have? How many valence electrons? So I'm going to listen down. A, titanium. B, iodine. C, radium. And D, manganese. Okay. So for this type of question, to find out the valence electrons, especially if we're dealing with things that are going to be in the transition metals, we have to understand our electron configurations, okay? So we're actually going to have a general one here that we're going to use for all of them. So we'll have the 1s, 2s, 2p, 3s, 3p, 3d, and manganese, just to find out where it is. Having a hard time locating it. Where's manganese? I did actually say, let me just refer to that. 25, I was looking too far. So radium is 80 something. Yep, radon is 86. So where is, oh, radium 88, there it is. Sneaky. And manganese is all the way here, 25. So, and we're gonna have now 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s, 7p. So this will be how it fully breaks down, because this should account for all the known elements in the periodic table so far. So first one I want to start with is titanium, Z22, so Ti, perfect. So how many valence electrons? It is one of them in the transition elements, but for titanium, as you can see, the way we go through this is we start counting from the top. So hydrogen, helium would count as your first 1s, so that one is complete. So titanium is 1s2, and then we keep going. So lithium and then beryllium, that would be now 2s2 complete, and we just keep counting through. Boron through neon, now that's your p subshell, so that would be 2p6, and sodium through magnesium, that would be 3s2, so this is completed. Okay, and then now we do the same thing here. Aluminum to argon, that's 3p6, and potassium to calcium is 4s2. Okay, so we've completed those. And then now titanium is actually going to be in the D subshell. And as you notice, we actually start with 3D. So it's not going to be a 4. Because when we get to the D subshell, it's going to be whatever row you're on minus 1. So we actually have here 3D2 for titanium. Okay? And if we just rearrange that, we have 3D2 for S2. Okay? How many valence electrons? We can actually just ignore all the parts that have anything less than 4, because 4 is our greatest number here. It's going to represent the electrons in the outermost shell. So with that being said, we look at the superscript that's attached to the 4s. And the reason why I say 4s plural is that if there are more 4 subshells, if there are more 4 orbitals, we would add up all of the superscripts of the ones in that 4 orbital. The only one here we have here is 2. So titanium, okay, would have 2 valence electrons. That would be the answer for that. Now let's use this same sheet to be able to find out about iodine instead now. Okay, so now iodine is all the way over here. It's quite low, and for this actually I'm going to use a different method here, okay, to be able to find its valence electrons, where we actually do what's called a noble gas. You can also just see it on your periodic table. Things like the column 17 is going to be have 7 valence electrons, but I actually want to show that with electron configuration, because this is the best way to go about it, because some will ask about transition metals and some will ask about things that aren't transition metals. So with that being said, the noble gas notation, okay, we actually start with krypton, because that's the previous noble gas, and what krypton has effectively said is that we're actually going to cancel all the way from, because iodine is actually on the 5th so we're going to actually finish every 4. So this is what we've done so far for krypton. Well, actually not just quite. We actually got all the way to here, about there. And the reason why I say that is because we actually just finished the 4p, that's where krypton is. And now we continue as normal, 5s2, because rubidium and strontium, so that'll be 5s2. And then to pass this whole d orbital, as you can see in the chart, it will be 4d10 based on the chart I showed you. And so that's 4d10, but iodine is all the way over here, so now we're back to the 5th number, so that'll be 5p5, because it stops on the fifth one. Okay, so if we rearrange this, it'll be 4d10, 5s2, 5p5. And like I said, 5 is the greatest number here, so that would be the last shell. This is kind of what we went through, and we went all the way and stopped at the 5p. So with that being said, 5 is the greatest one, so then we circle the numbers, the superscripts on the 5s, and we add them together. And just like how I said we were going to add them together, we have 7 valence electrons for iodine. For radon, okay, we're going to approach this the same way, where we're just going to use a shorthand. So we're going to actually start with radon for radium. Wow, very similar names. So we're going to start with radon for radium, okay, where we say Rn like that. And what we've effectively done, kind of like with the iodine, what we've effectively done is said, we're done with this, we're done with that, we're done with this, we're done with this, we're done with that, and we're done with this, and we're all the way over here. That's what that shorthand just meant right there, that we finished all the way to 6p. And now we're going to start with the 7th. So 7s, okay, francium and radium is right there. So we just have 7s2. And just as how we did it for the last one, circle it. That means this one has 2 valence electrons, okay? And now for the last one, manganese, okay? So just erasing all of these. Whoops. Let's just add this back. But now manganese, let's just also use a shorthand just to save us a little bit of time, because hopefully just by at least breaking the tin example, you kind of know how to navigate the electron configuration. So manganese, because the one prior is going to be argon, okay, we're pretty much saying that we're done with this, done with that, done with this, and done all the way to there, okay? So now, for manganese, we have 4s2, and then 3, because remember we jumped down 1 for the d orbital, 1, 2, 3, 4, 5. It'll be 3d5, okay? And that means that for this, we'll reorganize this. It'll be 3d5, 4s2. Manganese then will only have 2 valence electrons, okay? Because it finished that and then it just hopped into the d orbital, okay? So that's what we have. It's going to be 2, 7, 2, and 2 for this answer, okay? So with that being said, they kind of just went through where it was in the group, and close but no dice, because manganese in this case would not have 7 valence electron, it will only have 2. So, but the radium is correct, the iodine, oh no, yeah, radium is correct, the iodine is correct, and titanium is also incorrect, it would only have 2, which is why you stress the importance of the electron configuration. This is incorrect. Need to use electron configuration. And that is I guess the beauty of it. And you're probably wondering then, if it's, because you're probably noticing a trend here, is that it looks pretty straightforward, that your transition metals would just be the valence electrons of whatever is like out here in the first 2 columns. Most of the time, yes. But then you notice there's some examples, like exceptions, like chromium, for example. Because the d orbital specifically likes to be at least half filled if it doesn't take that much energy, well, you would notice that chromium would actually still have, instead of it being a typical 3d4, it would actually be 3d5 like manganese, but it got its 5 because now instead of having 4s2, it would be 4s1. So instead of chromium being 4s2 3d4, or I guess if we rewrote that 3d4 4s2, it would be 3d5 4s1, because now its d orbital is half filled throughout, and it prefers that, and it doesn't take too much energy to just use that one electron from its s shell. So something like chromium, for example, would actually only have one valence electron. Just things to be looking out for in regards to this question. And just to make sure that I'm not just making it up, valence electrons for tin. Whoops, that's not tin. That's titanium. That's the trickiest one. Yeah, so this, I would say this is incorrect because it's still basing it off of that. But exactly, you see here, they actually have it wrong as well because it would be 4s2 3d2, not 4d2. And here, valence electrons, interesting. But exactly, the configuration is 3d2 4s2. It only really has 2 electrons to work with in the valence shell. So with this, definitely I'll have to do a little more research because I would hate to be saying something that's wrong, but I'm quite confident in regards to at least the valence shell, because when it comes to things with bigger shells, aka like especially the transition metals, they're dealing with different subshells, and that's why, for example, the best way I can say it is that typically you can see tin 4, for example, as an ion, like where it's like 4+, but you also see the option of 2+, because of the fact that transition metals can have different in terms of their cations, because of the fact that they are transition metals and their valence shell works a little bit more wonky. But we're speaking specifically what it is, it's in its most outer shell, based on the electron configuration, titanium would have 2 and not 4. And same thing with manganese, it would have 2 and not 7. Okay, then move on to question 13 here. What is a molar mass of magnesium? Okay, so just a little bit of a break here in regards to that. So the molar mass of magnesium, okay, but notice how it's asking for molar mass of magnesium. Okay, so even though it's asking for molar mass, we have to first visualize what magnesium appears like just in its natural state, and you would usually just get Mn solid. Okay, the molar mass, it's the addition of the atomic mass constituents. If we only have just this, in the sense we're just going to add up 1 times Mn. So we look at the periodic table to get its atomic mass, and magnesium has 24.305 atomic mass units. That's all we have to add. So we end up with a molar mass of 24.305 grams per mole. Okay, and that is what we get for the molar mass of magnesium. Okay, that's really all there is to this question, just because we are adding the constituents to it, but because magnesium is just by itself, that's all we have to do for this question. Yep, so it is 24.305. This is correct. Okay, so now question 14. What is the symbol for an ion with 63 protons, 60 electrons, and 88 neutrons? So 63 protons, 60 electrons, and 88 neutrons. And then 50 protons, 68 neutrons, and 48 electrons. What is the symbol? So for this, I think they want us to write the isotope form for this. So with that being said though, 63 protons, that actually tells us what element we're dealing with, okay? So for that, okay, we have, just to make sure here, 63, element number 63, and that would be europium, okay? So now we know at least one piece of information, that we're dealing with the element europium, okay? 60 electrons, okay? Now, this actually tells us what type of ion it is, okay? Because based on the difference in charge, tells us the difference in charge. So there's 3 less electrons than protons, so 3. And with that being said then, because electrons are being removed, it'll be 3 plus. Okay, so it'll be EU 3 plus. That would be the first part, okay? But now, just because I want to be as specific as possible, I want to mix the two forms together. Exactly, we're saying this is still an ion, the 3 plus. But now we want to actually say what type of isotope it is. And to get that, we have to add the protons with the neutrons. So it'd be 63 plus 88, 151. This is what you get. Okay, you're saying that it is an ion, and you're saying what type of isotope it is. This would be your answer for the first one. And now let's see how we do it for the next one. 50 protons tells us that the element we're dealing with is 10, okay? And there's 48 electrons, so that's 2 less. And if it's 2 less, because electrons are negative, it's going to be now 2 plus, okay? And we still have the 50 protons here. And now, the last piece that we need is just the total number, like what the atomic mass units for this one would be. And that would be when you add the protons and neutrons, like we did for the last question. 50 plus 68, we have 118. This right here will be the ion for the second one. So we have the ion for the first one and the second one. Hopefully you saw how I was able to get all those numbers through what was given. It can seem relatively straightforward. Just remember that when you have less electrons, you form a more positive ion, okay? So exactly, 151, 63, EU 3 plus, and 118, 50, SN2 plus. So this is correct. So now for question number 15. What are the oxidation numbers of sulfur in each? So now this one is asking for the oxidation number, not the formal charge, okay? And to way we find oxidation number, there's actually a different set of guidelines and rules that we need to follow. Okay, so B is SO3, C is H2S, and D is CaSO3. Okay, so now for this, the way we find the oxidation numbers, okay, is that when we're working with each one, I'm actually going to give myself more, actually I'm going to write it here on the side, SF6, alright? So, halogens typically, and there are maybe a few exceptions here and there, but halogens typically have an oxidation number of -1, okay? Because it has an oxidation number of -1 and there's 6 of them, the total this has to account for is -6. So for this to have a total neutral charge, it is being shown, sulfur needs to be +6. And because there's only one of them, this oxidation number of sulfur here is +6. Okay? So that is the trick here, is that the goal for each of these questions that you want to use the given to give you the unknown. Okay? So SO3, right? Oxygen specifically, and this is specific to oxygen, likes to have an oxidation number of -2, except for like situations where it's like hydrogen peroxide, for example, to where in H2O2 where oxygen there is -1, but in most other cases it's -2, and there's 3 of them, so there's still going to be -6. So coincidentally, this sulfur here actually has the same oxidation charge of +6. Now H2S. All right, so with this being said, all right, okay, good. H2S, hydrogens, except for like in situations where hydrogen is like bonded with like another metal, for example, like LiH, lithium hydroxide. No, that's not it. Lithium hydride will be what it's called. Hydrogen typically just likes to function as +1, except for those conditions when it's bonded with metals. And here it's bonded with another non-metal, which is sulfur. And because there's 2 of them, that's +2. So in this case, sulfur has an oxidation number of -2. And now for the last one, this is kind of a little bit of a behemoth here, CaSO3. There are 2 ways to solve it, but the second way kind of needs you to know the your sulfates, sulfides, phosphates, and stuff, which is not really how you want to approach this, because sometimes if you don't know, you kind of get yourself lost. We'll approach it the same way with the givens, okay? Oxygen still likes the -2, and you know, that means it's going to be -6 in total over it. Calcium, because it's a metal, like specifically the alkali and alkaline earth metals, they usually just follow the periodic table in regards to what they like to do, which is give way to electrons. So that is what that means there. In fact, all these numbers you're seeing there, I realized I wasn't really explaining where I got them. Fluorine is -1 because it likes to just accept 1 electron. Oxygen really just likes to always accept 2 electrons. Hydrogen always likes to donate 1 electron, except for the situations, as I mentioned, where it's bonded with another metal. And calcium, in this case, always likes to donate 2 electrons. So for this whole thing to be a positive, a neutral charge, the sulfur here has to be +4. So that is what we have here for the oxidation number of the sulfur in each. And you're probably wondering, but wait, sulfur is like right under oxygen. How come it doesn't just go with the -2? That's why it's always good to just go with your givens, because those givens are written as givens because those are the ones that take priority in a sense. As you can see, sulfur kind of switched because based on what it was bonded with, it would take the lesser priority than whatever it was bonded with, and they would do their thing first, and sulfur would accommodate. Okay, so exactly as you see here, oxidation is +6 for sulfur in the first one. Second one is also +6. Third one, as you see here, is -2, and the fourth one, the oxidation is +4. So this is correct. And now let's move on to question 16. A carbon atom and a hydrogen atom form what type of bond in a molecule? What type of bond do carbon and hydrogen form? Okay, so for this question, actually, it really is just asking for this bond here, and you know what type of bond it forms based on the electronegativity, okay? Because the ranges, as it says, it states just what type of bond you get between an electronegativity difference of less than 0.4. This is a non-polar covalent bond, okay? Now, if it's between 0.4 and 1.6, this is a polar covalent bond. If it's greater than 2.0, this is an ionic bond. And now the caveat is between 1.6 and 2.0, and typically like anything else, if it's a metal and a non-metal bonded, that's an ionic bond. And if it's two nonmetals still bonded and it still creates like a value that's quite high, that will still be considered a polar covalent bond. So it depends usually what type of things are bonded with each other. So with all that being said, let's look at the electronegativity for carbon and hydrogen, okay? So carbon has an electronegativity of 2.55 and hydrogen has an electronegativity of 2.20. Subtract together to find the difference, and we get that the difference is 0.35. So it falls in the range here of the non-polar covalent bond, okay? So that means that carbon and hydrogen form a let me just write the answer in red, a non-polar covalent bond. Okay. And that is really the answer there. And as you can see here, they measure the electronegativity, and 0.35 difference is a non-polar covalent bond. Okay, so that means the electrons are shared evenly between them, relatively, and there's no poles formed in a carbon-hydrogen bond. So now question 17. Why are the molecules BF3, CF4, CO2, PF5, and SF6 all nonpolar, even though they contain polar bonds? So this is actually quite a bit of a doozy of a question. Molecules BF3, CF4, CO2, PF5, SF6, all nonpolar even though they contain polar bonds, okay? Even though it's polar bonds, okay? So the way they find out that they all have polar bonds is because as we're solving through these questions, you notice that we have to use the electronegativity to find out whether a bond is polar or non-polar, the electronegativity difference. So BF3, which is boron fluorine, right? The electronegativity for fluorine is 3.98, and boron is electronegativity of 2.04. And we subtract those two together, that is like, in fact, that's an ionic bond. That's quite a big difference there. And because it's a metal and a non-metal, that's an ionic type of bond. So how can it have this, but then it says, oh, but the whole thing is non-polar? Well, that one you actually have to know the Lewis structure. So for this, boron can only offer 3 electrons, and fluorine has 7, and there's 3 fluorines. But point being that the Lewis diagram, or just a Lewis structure, it would look like this. All right, and this the electron geometry for that, okay, is called trigonal planar, and it's coincidentally also going to be what the sorry, I'm blanking out, but it's coincidentally also what's going to be called the molecular geometry as well. And for these geometries, because it's like literally flat, think of it like, no matter how you look at it, exactly, like this is a flat molecule. We have the fluorines pulling on the boron all the same strength, because they're all the same molecule, making this whole thing, the net pull, the net momentum, net movement, which involves a little bit of physics, 0. It can't move anywhere because it's being pulled in all directions the same strength. And that is why BF3 is non-polar, even though it has very strong ionic bonds on each end. Now for CF4, that one is just even was it CF4? Oh, CF4. I was thinking CH4. But yeah, CF4 the difference between carbon and fluorine, so that's 3.98 minus carbon is 2.55. And by the way, to understand whether it's polar or not, the cutoff of difference, if it's greater than 0.04, that's when you start dealing with polar things. So this already greatly demolishes that as well. This is also a polar covalent bond. Okay? But CF4 is like, if you drew its structure, it would be like this. Okay? And it looks kind of strange, but if I were to draw it more so like, imagine you have a triangle base, and then the top here, this would be what you'd have. And you know how they say this triangle is the most solid shape because it has like perfect, balance in every corner and whatnot. No matter how you flip this base over, you'd end up with the same shape. Pretty much this molecule that's chilling in the middle there, okay, it's being pulled equally as well in every direction. In fact, this one here is known as a tetrahedral in both the electron geometry and molecular geometry. But the same thing here is being pulled equally in every direction. CO2, the difference between carbon and oxygen, okay, that is 3.44 minus 2.55. It's still like a 0.89 difference, which still passes the mark, so it's polar covalent. But this should be a little bit easier to see because what we have for CO2 is just that. And this is known as linear. And you can see this one a little bit more clearly that it's just getting the same pull in both directions. It's like just being stretched out like that, which cancels each other out as well. So that's why that one cancels each other out. PF5, that one, ooh, that one's quite big, but we have the difference between phosphorus and fluorine, okay, 3.98 versus 2.19, 2.19. Minus 2.19. It's very polar covalent. Still not, counts as ionic because it's still two non-polar molecules bonded together. But nonetheless, the way this one's going to look, PF5, is going to be quite the behemoth of a structure. Okay, but it's going to look kind of like, okay, like that. So still all polar covalent poles, but it's going to look like this, where you kind of have kind of like a circle in the middle here and a line that goes through it. So if you were to look at it directly from a certain angle, you would actually see it just looks like a plus, because this part here is a circle, all right, and this is the shape that is forming. So that would be what the shape looks like there. And because of that, everything here as well is also just experiencing the same pull. All these ones cancel each other out in the X plane, and these two cancel each other out in the Y plane. This is also known as a trigonal bipyramidal, okay? Because it kind of looks like you have the same type of pyramid thing, but instead of just being one, there's another dot down there. And they attach like that. It looks a bit more messy, which is why I like to just draw this picture instead. But this is what we're dealing with here, and the main middle part is kind of chilling somewhere in that middle. Okay, so that is why this one is also non-polar, because everything's pulling the same. And you probably can guess it with the SF6. SF6, that one is, to me, is kind of funny because literally think of it, it's actually just called octahedral. Okay, and the reason why is because, not because it forms like an 8 shape per se, but almost like that actually. It's the sulfur's in the middle, okay, and we have, well, the difference between sulfur and fluorine is that 3.98, 2.58, 3.98, 2.58, that's still going to be polar covalent. So that's way greater than 0.4 difference. So we have F here, and then we have kind of like this. So effectively now, instead of like that circle, we have a square instead, like a square sheet. Okay, and in the middle is going to be that line that goes through. So you still get that kind of plus sign when you look at it at a certain angle, because they're on the same plane. So all these will cancel each other out in the x-axis, and these two will cancel each other out in the y-axis. Why is it called octahedral? It's because kind of like when you draw it out, you have like the box shape here, and the point above. It's going to be really hard to communicate, but 3, 4. Same with the point below. 1, 2, 3, 4. Kind of like that. So that's why it looks kind of like the octahedral shape. I like it much better shown like this. But exactly, this is why all of these, even though they have polar bonds, they're all non-polar, because the key thing here is that when you actually look at their electron geometry and molecular geometry, you will see there that things are all being pulled in the same direction with the same force. Okay? Exactly. The individual dipole movements all cancel out. This is correct. All right. So with that, let's actually end it here. I just want to thank you again for joining me this morning. If you want to further clarify any of the things we discussed today, definitely check out the links in the description below. And once again, you have a great rest of your day. See you next time.